So today's video we'll be going over the variation of parameters. Now, unlike the method of undetermined coefficients, there were some limitations. The coefficients had to be constant as well as the family of a function had to be finite. Now, the variation of parameters does not have any limitations, which is why it's so useful. And so let's go ahead and do a problem. So for this example, we have y double prime plus y is equal to tangent x. So first off, let's go ahead and find the homogeneous solution. So we first get the auxiliary equation, r squared plus 1 is equal to 0. We see that r is equal to the imaginary I, and of course, with complex roots, this is the form that you get. And of course, with Euler's formula, you're able to represent with sine and cosine. So your homogeneous solution to the differential equation c1 sine x plus c2 cosine x. So now that we have that, we could go ahead and utilize this method. So we have our first function here, sine x. Let's call this y1, and our second function here, cosine x, let's call this function 2. So now from here, this is where we replace the constant c1, c2 with a function u with respect to x here. And this is where we utilize certain formulas, and we also utilize the Wronskian to be able to solve for these functions u with respect to x, which gives us our particular solution. So we have u1 with respect to x times sine x plus u2 cosine x, and this is where we utilize the formulas. So we have du1 dx is equal to negative function y2 times f of x. In this case, your f of x is your right-hand side of the differential equation. So in this case, it would be tangent x divided by the Wronskian, and the other formula is du2 dx is equal to your first function y1 times the fx divided by the Wronskian. So these are the formulas you're going to be utilizing to solve these differential equations. This is the variation of parameters. So let's go ahead and do that. So using the first formula, we have du1 dx is equal to negative cosine x times tangent x divided by the Wronskian. In this case, the Wronskian was negative 1. And from here, you can simplify it to just being sine x here, just sine x. So let's go ahead and do du2 dx. So we have sine x times tangent x divided by negative 1, and then you do some simplifications and you end up being cosine x take away secant x. Now in this case, since we have the du's with respect to x, we could just integrate these two and find the functions u1 and u2. So we finally have u1 is equal to negative cosine x after integrating, as well as u2 is equal to sine x take away log of secant x plus tangent x. Now, of course, the solution of the differential equation is always a linear combination of the homogeneous solution as well as the particular solution. So the homogeneous solution was the one we initially found out with the arbitrary constant C1 and C2, and the particular solution would be the modification of it with the arbitrary constants being this U1 and U2. So let's go ahead and write it out. So the solution to a differential equation is the homogeneous solution, which is C1 sine x plus C2 cosine x plus the particular solution, which was the u1 sine x plus u2 cosine x, which is basically cosine x sine x plus the sine x take away log secant x tangent x times cosine x, which is a pretty long solution, but this is it. This is the solution to a differential equation using the variation of parameters. Let's go ahead and do another problem. So for this second example, we have 4 double prime y plus 36y is equal to cosecant 3x. First, we get into standard form, so let's get rid of the coefficient for the y double prime here. So we have y double prime plus 9y is equal to 1/4 cosecant 3x. Now let's go ahead and solve the homogeneous solution to this differential equation using the auxiliary equation. So r squared plus 9 is equal to 0. We have r is equal to plus or minus I3, and of course we could get it in this form of cosine and sine, so this is our homogeneous solution. Now from here, our particular solution is going to be the function u1 y1 plus u2 y2. Of course, our y1 is this, our y2 is the sine 3x. All right, now from here we have the formulas that we previously used. First, I'm going to be solving the Wronskian. So you could go ahead and use this formula y1 times y2 prime, take away y2 times y1 prime. So the Wronskian ends up being negative sine squared 3x, take away cosine squared 3x is equal to, of course, negative 3. Now we just plug in in these formulas the du with respect to x. Of course, your f of x would be the right hand side of your original differential equation. You multiply and you solve for each, and then once you end up integrating, you have u1 is equal to 1 over 36 natural log of sine 3x, and u2 is equal to negative x over 2. So your particular solution would be the u1, so 1 over 36 natural log sine 3x times sine 3x, take away x over 12 times cosine 3x. And of course, we all know that your general solution to a differential equation is your homogeneous solution plus the particular solution. And so this is the variation of parameters method used to solve differential equations.